Welcome to the video for section 2.1.2, Autonomous First Order ODEs. So in this section, we're still not quite to the point where we're going to start explicitly solving differential equations, but we are to the point where we are going to start seeing how to analyze certain classes of differential equations. The definition of an autonomous first order ordinary differential equation is that it is one of the form dy dx equals f of y. So it's first order dy dx, and the autonomous business refers to the fact that the right-hand side is only a function that depends on y. There's no explicit dependence on x. Now you may think back to your first homework assignment and your first project, and you will realize, aha, I've already seen several examples of autonomous first order differential equations. So hopefully this section will make precise some of the behaviors you've already observed. The first thing we need is a definition, and again, this definition should look very familiar from the project. We say that a number c, a real number c, is a fixed point of an autonomous first order ODE if, any guesses? F of c is equal to 0. So when we plug c into f, we get 0. And in this case, we say that y uniquely equal to c, so the solution y equals c is a constant solution to our autonomous differential equation, first order differential equation. And you should convince yourself that that is indeed the case. Let's take an example. So our autonomous first order ODE is going to be dy dx equals y squared minus 3y. That I can, of course, factor to be y times y minus 3, and that right-hand side is my function f of y. So we check, indeed, this differential equation is first order, and it is autonomous because the right-hand side depends only on y. The first thing I'd like to do is find our fixed points. So I'm going to find my fixed points by finding c such that f of c is equal to 0. So f of c is c times c minus 3, and if I set that equal to 0, of course, that has the solutions c equals 0 and c equals 3. So my conclusion is that y equals 0 and y equals 3 are constant solutions. I claim, in fact, they are the only constant solutions. Why is that? Well, we know that if we have a constant solution to a differential equation, that means that its derivative is equal to 0. So if we plug y equals c into our differential equation, notice that's exactly solving for the fixed points of f of y. So we get exactly the two constant solutions, c equals 0 and c equals 3, and only those two solutions. Next question. If y is a solution to our differential equation, where is y increasing and where is it decreasing? And as you know from calculus and previous homeworks, the way we're going to determine where y is increasing and decreasing, we're going to look at the sign of the first derivative, the sign of y prime. And this should sound kind of familiar from calculus. We know that y prime equals 0 at 0 and 3, so I'm going to put these on a number line. I orient the number line up and down in this case to emphasize that these are y values. That was a mistake. I saw some on the first homework assignment. So I want to figure out in each region what the sign of y prime is. So if y is bigger than 3, then y prime is positive. So, and if y is between 0 and 3, y prime is negative, so y is decreasing. And if y is less than 0, y prime is positive, so y is increasing. And I mark that all on my number line. So the function, if it's increasing, I put an arrow facing up, and if the function is decreasing, I put an arrow facing down. Now, what is this information telling me? Well, let's take a look at some graphs of some solution curves and see if we can make sense. So you might already have some guesses about what this we call this a phase line portrait, what this phase line portrait is telling you. But let's see some solution curves. So I want to sketch some solution curves for my differential equation. I'll start with the two that I know explicitly a formula for, namely my constant solutions, y equals 3 and y equals 0. Now, on my picture before, I saw that my function, if y was something greater than 3, my function, my solution, is going to be increasing. So I get a solution curve that looks something like that, increasing as I move from left to right. If I had a y value that was between 0 and 3, that meant that my function was decreasing. So I have something that looks like this. And if y was less than 0, then I was increasing, and I have something that looks like this. Now you may ask yourself, how do I know exactly that curve in the middle seems to change concavity? How do I know exactly where that point changes concavity, where that curve changes concavity? Well, you can calculate the second derivative and check for yourself that that's exactly at y equals 3/2. So notice here, let's see, what should we notice? We should notice that if our solution, if our initial condition was just a little bit above y equals 3, then our solution curve in the long time behavior sends us far away from y equals 3, even if it was a little bit above or a little bit below. Whereas if our initial condition is a little bit above 0 or a little bit below 0, the solution curves tend towards the constant solution y equals 0. So in our picture a few slides ago, we had the number line with the arrows pointing in different directions. Those arrows are telling us something about the general trend of our solution curves. And we can make that behavior, we can make that phenomena precise, and we call it stability. So here's our definition. If we have a fixed point for an autonomous ODE, and I'll draw a few to show you the possibilities, the first possibility we could have is that our solutions tend to go towards that fixed point. So something like 0, y equals 0 in the previous slide. We call those types of fixed points, we call them stable, or we sometimes call them attractors. If our fixed point is more like the fixed point y equals 3 was in our previous example, so on either side of our fixed point, our solutions are moving away from the fixed point, we call that unstable. We might also call it a repeller. And if the behavior near the fixed point is heading in one direction and heading out in the other direction, then we call that semi-stable. So given all this information about autonomous first-order ordinary differential equations, we can fully classify and understand the solutions even if we can't get an explicit formula.